Good morning. So welcome. This is the third session of our monthly seminar. And today, it's an interinstitutional seminar that is organized here in Miami, in France, and also in Chile. And today we are going to have the pleasure of listening to Carolina Araujo, a researcher here from IMPA, who will speak about the birational geometry of Calabi-Yau pairs. Before I give the floor to her, let me just say that for those that are attending the talk via Zoom, feel free to ask questions. We have a connection direct with our our sound system here in the auditorium, so we are going to listen to you if you interact. There will be no one looking at the Zoom, so it will not work to raise the hand or anything like that. You should just make noise, just speak, and we are going to answer and we're going to interact. Okay? So after that, let me just welcome Carolina and please, enjoy.
Thank you, Jorge. So first of all, I would like to thank all the organizers for the invitation and also for the flexibility. This talk was supposed to take place last week, but it had to be postponed. So thank you again for being patient. So today I want to talk about birational geometry of Calabi-Yau pairs, and hopefully I will convince you that there is some relationship with hyperbolicity. So before I forget, let me say that I will be always working over the complex numbers, and I will try to make sense of birational geometry of Calabi-Yau pairs. So let me start by discussing the notions of pairs. So why should we look at pairs in algebraic geometry? So nowadays, this is a mainstream approach. In algebraic geometry, we often work with pairs from the beginning. But maybe for those that are not so used to this notion, let me give you one historical motivation for the study of pairs. So this starts with Iitaka's program from the 70s, which had the aim to study the birational geometry of open algebraic varieties. So the idea is that you start with, say, U, a possibly open, complex algebraic variety. And Iitaka wanted to develop a birational geometry for such varieties in a similar way to that done, say, for surfaces, for projective surfaces. So, for instance, one would like to define codire dimension, plurigenera, irregularity, and so on. Of course, for open varieties, this is much more complicated. We can't just look at the, say, sheaves of differentials on this open variety. So the way that Iitaka proposed to handle this is the following. So you start with your open variety, and then you compactify it to a projective varieties X. And then by using Hironaka's resolution of singularity, you can even assume that this compactified variety is smooth. And moreover, you can assume that the complement, so let me call it X, the complement of U, so this is what we call the boundary that we add to this compactification, is a simple normal cross in the divisor. So I would just denote it like this. Simple normal cross and divisor, and then the idea of Iitaka is that instead of to study U, we study the pair X, smooth projective variety, and B, simple normal cross and divisor. So I think Iitaka calls this a smooth compactification, a compactification with smooth boundary for U. And so the idea is that then in order to study U, we study this pair. And so probably this is one of the first occurrences of pairs in algebraic geometry. And then the way that Iitaka proposed is to look at the sheaf of logarithmic differential forms So this is the sheaf of differential forms that have a logarithm pole along D. And then he studied these sheaves, and it turns out, so he proved this very nice theorem. He showed that if you look at, say, the space of global sections of these logarithmic differentials, this does not depend on the compactification with smooth boundary. So, for instance, this will allow us to define plurigeneral irregularity, and also, for instance, let me just state this for the Kodaira dimension. So this is from Iitaka, sorry. So he showed that the Kodaira dimension of the pair XD does not depend on the compactification with smooth boundary. So if you take another smooth compactification of smooth boundary, then the value of this Kodaira dimension is the same. And so he defined this to be the Kodaira dimension of the open variety. And okay, so it makes sense to define the Kodaira dimension for a smooth variety, and then it makes sense to study this notion. So let me just give you some examples. So let's look, for instance, now the interesting thing is that even though now the compactification has a lot of freedom. For instance, let me just give you an example what happens in dimension 1. So let's take what happens when x is equal to p1. And then so U is an open curve, a rational curve. And now here there is the following possibilities for the Kodaira dimension of the pair. So the Kodaira dimension will be either minus infinity or 0 or 1. And this will be minus infinity if and only if. Now here D, so let's see how I wrote this in terms of U. So this is U, either U is P1 or C. The Kodaira dimension will be 0 if U is C star. And otherwise, the Kodaira dimension is 1. So this is for dimension 1. Let me also explain an example in the case of dimension 2. Here, I want to take now x to be P2. And for simplicity, I will take the divisor D to be a union of lines. So this is L1 plus up to LR. So let's call them all, suppose they are all lines. Then, again, we have a classification of the Kodaira dimension of the open variety. It can be minus infinity, 0, 1, or 2. And again, there is a classification. So the Kodaira dimension is minus infinity if and only if this divisor consists of lines all passing through a point. Doesn't matter the number of lines. And then it will be 0 exactly when we have this configuration of lines. And it will be 1 if we now, again, we start with this configuration and then we add more lines passing through this intersection point. Here we need to have at least 4 components. So here R is at least 4. And then otherwise, the Kodaira dimension is 2. Okay, so these are just some examples to see, and then we see that even for highest Kodaira dimension, when we look at the compact variety, the projective variety, this may be, say, a funnel variety, which is usually a negative Kodaira dimension. Okay, so So we can also, from this point of view, we can also define notions of hyperbolicity for pairs. So let me take x and d as above. So for the moment, let me take x smooth projective and d simple normal crossing divisor. Soon I will relax this assumption, but let me look at this case for the moment. I can define the notion of hyperbolicity for these pairs. So so here I am using, I'm following the definition of Liu and Zhang. So they propose the following notion. So here let me write D as sum of the components di, the reducible components. So they define the pair xt to be broadly hyperbolic, and also they introduce the weaker notions of Mori hyperbolic. Well, if the following holds. So the definition is similar to the usual definition of Brody hyperbolicity. So if this is their hyperbolic, if there is no non-constant map, well, the type of map here will depend on the type of hyperbolicity. So this so there is no non-constant, either holomorphic or algebraic map. Morphism, non-constant morphism from C to the complement of D. And not only that, so this is just the first condition, but we also want to require the same for the open strata of D. So let me write it here. And the same holds for the open strata of D. So what do I mean? What I mean by this is that if I look at the pair, let's say DI intersect sum of J different than I of the dj. And I do the same for the I intersect dj and so on for all this open strata. So this is the notion of Brody or Mori hyperbolicity for pairs. And here, again, there are some results and conjectures. So let me just start with a conjecture, which is known under some assumptions, that if a pair xd is Brody hyperbolic, then kx plus d is ample. So as far as I know, this is the general case is still open. But for the Mori hyperbolicity, more is known. So this is a theorem of Svaldi from 2019. It says that if xd is Mori hyperbolic, then the log canonical class kx plus d is NIF. Okay, so this is just to give you some context, I would like to make 2 remarks about generalizations of these notions. So first of all, the first remark I want to make about flexibilizing this condition that I asked that X is smooth and D is a simple normal crossing divisor. So there is now a very extensive theory of what we call singularities of pairs. So this is developed in the context of the minimal model program. So within the minimal model program, there are many more reasons for us to consider pairs. So I just gave you one motivation, but it's from the point of view of the minimal model program, it's absolutely necessary to work with pairs. And then here, for this, one had to define and develop a framework to study the singularities of this pair. So now we have a very well-established theory. There are various notions of singularities for pairs. Maybe the ones that we are going to encounter are log canonical and canonical. And the prototype for those is exactly this situation that we are considering. So a smooth projective variety together with a simple normal crossing divisor is the prototype of a log canonical pair. So for canonical, you have to take a smooth projective variety together with a D, an irreducible, smooth hypersurface. And this would be an example of a canonical pair. So, but this is an extensive theory. And this is the first generalization. We drop that simple normal crossing condition and allow, say, for pairs with log canonical singularities. And then this definition of Brody and Mori hyperbolicity can be extended to this case but you have to do the stratification that one gets here is slightly different. It's related to non-KLT locus or log canonical locus, log canonical centers. But I don't want to say too much about that. And the other remark that I just want to mention is that here we are considering divisors are veil divisors. So this is really a sum of prime divisors on X. But in birational geometry, in the minimal model program, one is led to consider a much more general notion of Q divisors. So here, the coefficients of D are allowed to be rational numbers, say, between 0 and 1. And again, this is absolutely crucial in applications to the minimal model program. And again, these notions can be also extended to this more general setting. But for the sake of this talk, I think we can stick to the simplest situation. Okay, so now I want to address, maybe it's a good time to ask if there are some questions. Okay, so now I want to address the following question. So now we know that we have a pair, say a Calabi-Yau, a log canonical pair, and we can associate to it a Kodaira dimension and even more other invariants to this pair. But now, how actually do we make sense of the birational geometry of a pair? So let me put this as a question. So how to make sense of the birational geometry of a pair. In other words, if I have two pairs, what are the birational maps, the relevant birational maps that I should allow or study between them? And I don't have a clear answer for that, but what I would like to discuss now is I want to to focus on a very specific type of pairs, which I called Calabi-Yau, we call Calabi-Yau pairs. And then for this class of pairs, I claim that there is a very natural notion of what would be the birational geometry of this pair. And so this is what I want to discuss now. So let me move now to Calabi-Yau pairs. So I will usually just write abbreviated by CY, Calabi-Yau pairs. So let me define what I mean by a Calabi-Yau pair. So for me, a Calabi-Yau pair is a pair XD where, again, now I will relax a little bit the assumptions on X. I will not require that X is necessarily smooth, but I will ask that X is a terminal projective variety. D, again, for me now, D will always be a veil divisor. So this is really a sum of divisors with integer coefficients. And I will require that this divisor is such that kx plus d is linearly equivalent to 0. So this would be the case of Kodaira dimension 0. And I will now have to also impose some, I imposed some restrictions on the singularity of the ambient space, but I will also impose restrictions on the singularity of the pair, and we require that the pair is XD is log canonical. So for now, at least for the next 20 minutes or so, you can think of this as being a smooth projective variety together with a hypersurface, possibly reducible hypersurface, anticanonical hypersurface. And so this is the notion of a Calabi-Yau pair. And what I will try to convince you now is that at least for Calabi-Yau pairs, there is a good notion of what are the birational maps that one should consider between Calabi-Yau pairs. So before I introduce this, let me just make a remark. And this is what makes things special about the Calabi-Yau condition. So whenever you have a Calabi-Yau pair, this condition here is telling us that there is a essentially unique up to scaling volume form, omega d. So I will always denote the space of volume forms here. Let me say that the dimension here is, let me fix the dimension to be n. So I will denote the volume forms on X, the space of volume forms, rational meromorphic volume forms in this way. So there is a unique volume form on X that does not vanish and that has a simple pole along D. So let me express this by saying that the divisor of this meromorphic volume form is just minus D. So it does not vanish, and it has a simple pole along D. And now the existence of this unique form gives us a hint on which birational maps we should consider between Calabi-Yau pairs. So let me give you the definition now. So let's say that we have two Calabi-Yau pairs. So we take X dx and Y dy, two Calabi-Yau pairs. And we want to distinguish some special birational maps between them. So let's start with a birational map between X and Y. So birational map. So whenever I have a birational map between these two varieties, I have an induced identification of the space of volume forms. So this F will induce an identification of the space of rational volume forms on X and the rational volume forms on Y. And we will say that a birational map is volume preserving for these Calabi-Yau pairs if this identification here preserves these special volume forms up to scaling. So let me give you now the definition. So we say that F now is a map of pairs, is volume preserving so I will often abbreviate it by VP. If this identification respects this special norm form. So if F star of omega xd, omega dx, is just up to scaling, let's say, lambda times omega dy. And I claim that this is a good notion to consider in this category of Calabi-Yau pairs. And before, well, let me just give you maybe just one remark to say that there is a good reason to consider this. This type of maps, they're very easy to study with the tools from the minimal model program in birational geometry. So there is a nice valuative characterization of this notion, which can be stated as follows. So we suppose that you have a birational map between X and Y, and you want to decide whether it is volume preserving or not. So what you can do is, so you have this birational map, F. You can take some resolution, some log resolution of this map. And for any such log resolution, you can take a prime divisor E on W and compute the discrepancy of E with respect to these two maps, to X and to Y. So the condition, the volume preserving condition, is equivalent to saying that these discrepancies are all the same. And so this, as I said, this allows us to use all this technical tools from the minimal model program to study this notion. And then once we have this notion, in particular, we can define the group of volume-preserving self-maps for a given Calabi-Yau pair. So let me give a notation for this. So we define the birational group of a Calabi-Yau pair. So XY is a Calabi-Yau, XD is a Calabi-Yau pair. Then I can define the notion, the birational group of the pair, to be the group of birational self-maps of X, which are volume preserving for this pair. So F as a map from the pair XD to itself is volume preserving. And this is the group that we will be interested in. So let me give you some examples. Let me give you one very nice example that was computed by Jeremy Blanc. So here we are going to take xd to be P2 together with the complement of the torus, so the union of the three coordinate lines. So this is, here in this case, you should think of the open variety U as just being the two-dimensional torus. Now, in this case, so this was a theorem by Blanc. So Blanc proved this. This was proved by Blanc. I don't remember, sorry, I forgot to note the year. But Blanc computed that the birational group of this pair, which he called symplectic group of the symplectic birational group of the plane. So this is generated by, well, here you have the torus, which acts in itself by translation. So here, this will, again, this will induce volume-preserving birational maps of xd. You also have an action of SL2Z, so acting by monomial transformation. So here I take, if I have a matrix, maybe I write this here. If I have a matrix A, B, C, D, with integer coefficients, it will send a point, let's say in affine coordinates, I can send it to XA, YB, XA, YB, and XC, YD. So this is this SL2 actions. And then this part here of the group is the part that actually preserves the two-dimensional torus. But this is not enough to get the full birational group of the pair. Here you have to add one more generator, a birational map of order 5, which I will just write it in affine coordinates, can be written in this way. So this is y1 plus y over x. So this is a birational self-map of P2 of order 5, and this is the full group, birational group of the pair. Now, even in higher dimensions, so for you have the same, you could ask the same questions for Pn and the union of the coordinate hyperplanes, and for those, it's not known what the birational group is. So I think I don't even know if people have a conjecture of what it should look like. But okay, so now what I want to do for the rest of the talk is to explain to you a framework, a very efficient framework to do explicit birational geometry for Calabi-Yau pairs. So here what I mean is, like in this case, I have an explicit example of a Calabi-Yau pair, and I want to write down exactly what is the birational group of this pair. And for that, we have a very nice tool, which is called the Sarkisov program. So let me just do a digression, and maybe before I talk about this for pairs, let me discuss this in the classical context first. So we go now to the Sarkisov program. Then I will explain how we can use this to study the birational geometry of Calabi-Yau pairs. Okay, so here, let me, to start in a concrete way, let me start with the classical Cremona group. So let me start by looking at the group, the Cremona group, the group of birational self-maps of Pn. So this is classically called the Cremona group. And this is a huge and super complicated group. So now a lot of people are very interested. I'm very fond of this group. But it's huge and it's very complicated. Now, even in low dimension, so if you take dimension, say n equals to 2, so birational, the group of birational self-maps of the plane. So here we have a very classical theorem. So this is from the still 19th century. So this is it's called the Nether-Castelnuovo theorem. So this is from, well, we put some dates here. And it says that in dimension 2, the Cremona group has a very simple description by generators. So the Cremona group in dimension 2 is generated by, well, first you have the automorphisms, the linear automorphisms of P2, the PGL3. So let me just write it, the automorphisms of P2. And then you have to just add one non-regular birational map to generate the whole group. And this is exactly what we call the standard quadratic transformation. So the standard quadratic transformation is the quadratic transformation in the plane that takes x, y, z to their inverse, or in other words, to y, z, x, z, and x, y. So with the automorphisms, which are maps of degree 1, and this map of degree 2, you generate the full group of Cremona transformations. You may think that because it has such nice generators, it would be easy to describe this group, but it's actually not true. There's a lot of activities on understanding this group. But in higher dimension, things are even more complicated because we do not have such nice, so you can think of this as a nice factorization theorem. So whenever you have a Cremona transformation of P2, you can compose it, you can write it as a composition of automorphism with this nice quadratic transformation. So in dimension, starting in dimension 3, this is not true. So Hilda Hudson in the 20s, so let me see, Hilda Hudson. So in 1927, she already showed that you cannot, in dimension at least, so here now dimension at least 3, you cannot have a set of generators of bounded degree. So this group does not admit a set of generators of bounded degree. So this is very different from the two-dimensional case. So you see, in the two-dimensional case, we're saying that the Cremona group is generated by the maps of degree 1 and one element of degree 2. So here, there's no way you can do this in higher dimensions. And moreover, as far as I know, there is not even a known nice set of generators. So we don't describe this group by generators. However, there is a very efficient way to study this group by a means of a, let's say, a weak factorization program. So this is what we call the Sarkisov program. So let me explain the idea. So the Sarkisov program so in dimension 3, it was proved by Corti in 1995. So this is dimension 3. And in higher dimensions, it was a theorem of Haken-McKernan more recently, so in 2013. say they prove the following weak factorization for the Cremona group. Actually, the result is more general, but for simplicity, let me first state it for the Cremona group. So the idea is that you start with some birational map, self-map of Pn, and you would like to factorize it in some nice way. So what the program tells you is that there is a factorization into simpler birational maps. But now you have to be careful here because the intermediate varieties may not be Pn itself. So instead, what they are not really a variety. They are what we call a Mori-fiber space. So this is a certain projective variety together with a fibration structure. In this case here, the fibration is just to a point. And so these intermediate varieties, let me call Xi, Ti, is what we call a Mori-fiber space. So I will abbreviate it in this way, Mori-fiber space. So these are possible outcomes of the minimal model program applied to some variety, some rational variety. So if you start with some rational variety, you apply the minimal model program, you may get to Pn, but you may get to many other possible outcomes. So these intermediate varieties are precisely these possible outcomes of the minimal model program. And these simpler maps, I don't want to define them precisely, but let me tell you what they are. These simple maps, phi I, this is what we call a Sarkisov link or an elementary link. They do admit a precise description, which I will not give you, but I will tell you what they are. So if you think of each one of these Mori-fiber space as a possible outcome of the minimal model program, so remember that in the minimal model program, at each step you have to make a choice, and then depending on the choice, you get to different outcomes. So the idea of the elementary link is that if you think of this as the last step of the outcome of the MMP, you go one step behind, you go back one step and make a different choice. And then you will get this composition is exactly what we call the elementary links. So this is the usual Sarkisov program. So more generally, what the Sarkisov program, the Sarkisov program is not, here I stated it for Pn, but it works for any Mori-fiber space. So it says that any Mori-fiber space, any birational map between Mori-fiber spaces can be written as a composition of Sarkisov links. So this turns out to be a very useful tool to study the Cremona group, and much of the recent progress has been obtained using this, exploiting this program. And we have, and for Calabi-Yau pairs, now I want to go back to Calabi-Yau pairs. It turns out that for Calabi-Yau pairs, we have a version of the Sarkisov program. So this is a later theorem by Corti and Kalogyiros. So from 2016. And their theorem says that any volume-preserving map between Mori-fiber Calabi-Yau pairs can be written as a composition of Sarkisov links. So any volume-preserving birational map between not Mori-fiber spaces, but Mori-fiber Calabi-Yau pairs is a composition of volume-preserving Sarkisov links. So is a composition of volume-preserving Sarkisov links. So what this means is that we have exactly the same diagram as we have here. So let me just start. Yeah, now we are starting with a Calabi-Yau pair X, the X, but I assume it also that it has some structure of a Mori fiber space. And I have here, again, another Calabi-Yau pair, which again has also a structure of Mori fiber space. And now suppose that I have a volume-preserving birational map between them. Then what the theorem says is that I can write this as, again, a composition of Sarkisov links, but now at each, the only difference is that each variety, each intermediate variety, admits some divisor D, making this a Calabi-Yau pair. And so on. And now, maybe this looks like just okay, could be an interesting generalization, but I should say that in a sense, this version of the theorem is much easier. It's much, in a sense, it's much, it gives much more information than this one. It's much, so let me just give you an explicit, precise statement. So for instance, if you want to use this theorem, say, to study the Cremona group, the birational maps of Pn. So if you are here, you want to study all the birational self-maps of Pn. In particular, you would, in order to apply this theorem, you would need to understand what are all the Sarkisov links starting from Pn. And this is not classified in dimension, starting in dimension 3. So let me just put it as a remark. So if you want to understand the Sarkisov links starting from Pn, so you're starting from Pn to a point and go to some other Mori fiber space, x1, P1, these Sarkisov links are not classified. Even in dimension 3. So in dimension 3, maybe one can say that we are, in a sense, very close to a classification, but still, even in this case, we do not have a full classification. On the other hand, this is one point, but on the other hand, dependent on D, dependent on the complexity, on the complexity of the boundary divisor D, this, the volume-preserving Sarkisov links starting from Pn with this, say, this is, I'm assuming that this is a hypersurface of Pn of degree n plus 1, so that this xd is a Calabi-Yau pair. Now, if you want now to apply the volume-preserving Sarkisov program, you would want to classify these Sarkisov links between Mori-fibered Calabi-Yau pairs. And now, depending on D, the volume-preserving Sarkisov links starting from this are much easier to classify. So can be classified. Can be classified. So in a sense, this volume-preserving condition is very restrictive, and so it gives us more information. So in order to illustrate this, let me just state two theorems that I proved together with Alessio, Corti, and Alex Massarenti. So we've been actually using this theory to actually do some explicit birational geometry. So this is, so the first theorem that I wanted to discuss. So this was with Alessio, Corti, and Alex Massarenti. So we consider the following situation. Let's take a hypersurface in projective space of degree n+1, so that this is a Calabi-Yau pair. And let's take this hypersurface general hypersurface. Then, if we want to understand the birational group of the pair XD, hypersurface here, of course, of degree n+1, so that it is a anticanonical hypersurface, then this group here is not interesting. So this is just the group of automorphisms of X that preserve the hypersurface. So not much.
What is X?
Sorry, here X, I'm taking X to be Pn. Thank you. So I'm just looking at the pair Pn with a hypersurface of degree n+1. And in fact, okay, I am stating it in this way, in this simple setting, but our result is more general. You can take any terminal variety of Picard number 1 and consider an anticanonical hypersurface. And again, if it is general, here general, of course, in order to study the most general situation, we have to make general more precise. And in this case here, general means that D is smooth with Picard number 1, with sort of Lefschetz type condition. So and then once you take these precise conditions, you can generalize this. And the way that we prove this is, what we do is we look at this situation here. Suppose that we have a volume-preserving birational self-map of the pair. And then let's look at the first link. And then what we show is that, and this is what I mentioned here, is that if the D satisfies these nice conditions, there is no Sarkisov link to start with. And so there is no possible Sarkisov decomposition, volume-preserving Sarkisov decomposition. So there is no links from Pn with a general hypersurface. And then, well, then we wanted to investigate, then, okay, let's then, instead of taking D general, let's make D special. And then from these conditions, there are two different directions that you could take. You could take, let's say now in P3, you could take a quartic surface, a K3 surface, either allow for singular surfaces or allow for a higher Picard rank. So this, we have investigated those cases. So what we did first was to look at the case of singular quartics, and then again, using the volume-preserving Sarkisov program, we could have a very explicit description of the group. So here, maybe the second theorem that I want to discuss. So now we take, instead of taking a general smooth hypersurface, we take a hypersurface in P3 of degree 4 with simplest possible singularity. So we take now P inside P3, now a general quartic hypersurface with a singular point. Well, if we take them general, so if you take a general singularity, it will be an A1 singularity. And in this case, again, we could compute the birational group of P3 with this boundary. And now it's very far from being trivial. And actually, we computed this rather explicitly. So we wrote this group. We gave it a presentation as a semi-direct product of a group G that I will describe, and Z mod in the cyclic of order 2, where this G is what we call a form of Gm over the function field of P2. So what this means is that this is an algebraic group defined over the function field of P2, such that over the algebraic closure it becomes GM. So this, and in fact, if you give me a precise equation for this quartic, I can write down all the birational maps in this group. So this is very explicit. And again, the way we do it is now we consider this more complicated, more complex pair. We characterize, we classify all the links that start with P1. Now there is a possibility you can blow up the singular point. And then we go to the first Mori fiber space. And again, what we do is we classify all the links that we can construct from this pair and so on. And so in the end, we are able to give this complete description. And okay, so maybe since I have 4 minutes, let me just try to explain another application of this tool that I have been exploiting recently, which has to do with automorphisms of the smooth hypersurfaces. So let me just give you a last application. So let me start by motivating this with a classical theorem of Matsumura and Monsky. So here the context is the following. Now let me take X, a smooth hypersurface in projective space of degree D, so smooth hypersurface. And I want to understand the automorphism group of this hypersurface. So there is this very nice theorem of Matsumura and Monsky that says that except in two special cases, so except if n the dimension and the dimension of the hypersurface is the degree, except in the cases when it is dimension 1 and degree 2, so degree 3, so an elliptic, a cubic curve in P2, or a quartic surface in P3, so except for these two cases, then every automorphism of the hypersurface is the restriction of a automorphism from the ambient space. So in other words, let me just say this in symbols. So if you look at the group of automorphisms of the projective space that stabilize the hypersurface, this group surjects by restriction onto the automorphism group of the hypersurface. And now, now we are led to consider these two exceptional cases. And the first one is the case of the elliptic curve in P2. Well, let's look at those exceptional cases. So the first exceptional case is the case NB is 1, 3, so an elliptic curve in P2. And in this case here, there's no way that we could have that surjection because the automorphism group of the elliptic curve is infinite, while the group on the left-hand side would be finite. On the other hand, we can still describe this automorphism in terms of the coordinates of P2, because if you look at the group of birational self-maps of P2 that stabilize the cubic, this surjective into the automorphism group of C. In other words, every automorphism of the cubic curve is induced by a Cremona transformation of P2. And now, what about the case? So this was the first exception. And what about the next exception? So quartic curves, quartic surfaces in P3. So here, can we expect the same? Could it be possible that every automorphism of the K3 quartic surface is induced by a Cremona transformation of P3? So let me so this problem, I think it was first posed by Giza-Tooling. So he asked the question, let me put it this way, when the same here is true in the case of quartic surfaces. So when we get a surjection between the group of birational self-maps of P3 that stabilize a quartic surface into the automorphism group of the quartic. And so this is a problem that I'm currently investigating together with Daniela Paiva and Socrates Zikas. Still an ongoing project, but let me just mention our current results. So if you have a smooth quartic surface in P3 as a K3 surface, so we know that its Picard rank is between 1 and 20. The case of Picard number 1 is very simple, because in this case, the automorphism group of the quartic surface is trivial, so there's not much to do. And those things start to get interesting when the Picard number is bigger. Then you have more structure for the automorphism group. And so in a recent paper with Daniela Paiva and Socrates Zikas, what we do is we completely solve this problem in the case of Picard rank 2. So a complete solution in the case when the surface has Picard rank 2. And our approach, again, is the same. We exploit this, the volume preserving Sarkisov program, and in particular, so we start with our given Calabi-Yau, Mori-fibered Calabi-Yau pairs, and we classify all the possible links, or at least we give some description of the possible links that we can start from this pair. And then this led to a solution in the case of Picard rank 2. Picard rank 3, well, things get much more complicated, and there's still lots to do. So I guess I will stop here. Thank you for your attention.
Thank you, Carolina. We have some space for questions and comments. So,
in this theorem, what general means? Because in the previous one, was smooth and Picard rank 1, right?
Yes. So here, what we want is general means that the singularity. So general here means that the singularity is an A1 singularity, and again, the Picard rank of S is 1.
Okay, thank you.
Other questions? People that are following the lecture online are also free to ask questions. Just speak, and we are going to listen, if that's the case. So.
What shape in positive characteristic?
Very good question. So, unfortunately, I have no results in positive characteristic. But it is, I think it's an interesting, theory to develop also in this context.
Eduardo?
Yes, I was going to ask how the quartic is singular.
So, if the quartic is singular, then we have these results for the simplest case. So now you have to be a little bit careful, because once the quartic is singular, you should not really look at the automorphism group here. You should look at the birational self-map of S. Here, everything is the same because it is smooth. But in this case here, if you have a singular quartic surface, a general singular quartic surface, the automorphism group is going to be this part here. It's just an involution. You can project from the singular point. This gives you a 2-to-1 map to P2, and then the ramified, the involution associated to this ramified cover is the generator of the birational map of the quartic. And so this gives you actually a surjection of this group onto the birational group of the quartic, which is in this case very simple. It's just this part here.
Any further question? Well, if that's not the case, let's thank Carolina again. So the next talk will happen in INSA, Miami, and will be next February 28th. It will be a talk by Ludmila Kamenova. We are going to send you an announcement soon. Okay, thank you.